Okay, so if it's all right for Jean, we might spend 50 minutes and finish off this section, which is on describing functions, and then if there are one or two questions, which I'm sure there won't be, on your assessment next week, or this week, then we can spend the rest of the time looking at questions you might have, and obviously what the answers to those might be. Is that all right? Yes. Okay, so to finish off the section on describing functions, I guess, and to start off by recapping where we were, where we finished off last week, we were looking at the concept of a describing function. So the purpose of them is to linearize nonlinear elements, or it's one way. There are different ways in which we can go about linearizing nonlinear elements, but the idea is that the theories that we have, such as Laplace and stuff, only apply to linear systems. So if we have nonlinear elements within our loop, we need to linearize them in some way. So describing function is one way where we're looking at frequency. So we're taking, considering the input signal to consist of a sinusoid. We're checking to see can the output be approximated by a sinusoid, and if it is, if that's the case, then we can come up with an equivalent linear gain for our system. We talked about that in order to do this analysis, there must be 4 assumptions must be valid, or we must be able to establish that these 4 conditions apply, so that we have a closed loop system which can be composed into, or broken down into 2 elements. We have a linear element and a nonlinear element. That, as I mentioned, the input to the nonlinearity is a sinusoid, that the output produces a periodic response, and then that the process, if you like, that we're, actually I don't have it there, it's on the next slide, the process that we're considering, this guy here, has a low pass characteristic. So if we're thinking of, so in order to establish that, we're thinking of our Bode plots, for example, and a low pass characteristic. If we look at the amplitude part of that, what we're saying is we'd expect the gain, for example, if it started at 0 dBs, as we go up in frequency, that the gain is going to start doing something like this. Okay, so the gain of the system reduces or attenuates as we go up in frequency. And the argument for this happening is that the low pass characteristic then cuts off any high frequency elements that are generated by our nonlinearity. So this is our simple nonlinearity. With high frequency elements here, this low pass filter chops them out, and therefore we have, if you like, a single frequency going in and a single frequency coming out, and therefore it's possible to linearize it, because that's one of the definitions of a linear system, is one frequency in and one frequency out. So the sorts of question which you could get on this in terms of an assessment is here. This is one, I didn't write it, but it was, I don't think I wrote it anyhow, but it's typical of what could be asked. So A, for example, in nonlinear systems, define what's meant by a describing function. That's slide 2 there, basically. That's the notion of a describing function, that we're dealing with nonlinear elements. And the idea is the describing function is one way to address those by looking at the ratio of our input and output signals. B, with reference to an example, so describe the main steps involved in applying the describing function. So we're talking about those 4 steps on slide 3. Okay, so this is the assumption. It can be decomposed into linear and nonlinear elements. The input is nonlinear, the output produces a periodic response, and we've got a low-pass filter.
Are you referencing an example? What are you?
In that context, we'd probably talk about something general like this. So the example should be relating, an example non-linear element. So you'll be talking, for example, in a relay. You know what I mean? So it's not really meaning that you have to take like an industrial example in terms of what the process would be, but that we'd have a closed loop system which would be represented like by this, the assumption is that in here we have a relay, here we have a plant or process of some description, and in fairness, most of the analysis, or most of the elements, are quite general anyhow. So it's like that the input to the nonlinearity is a sinusoid, that the output produces a periodic response. So you could talk about that then in the context of the relay element. That if with our relay, if the input is greater than 0, so if our input is greater than 0, our output is going to be positive. When our input is less than 0, it goes negative, and therefore you're going to get that square wave coming out, which is periodic and so forth. So the two bits that I want to focus on today are the calculations associated with C and D, or I guess the analysis associated with parts C and D of that question. So given that the closed loop system of figure question 1c, given the closed loop system, determine the amplitude and period of the signals y of s and u of s. Right? And you may assume that the input r of s is 0. So we're assuming that our reference is 0 over here, and you're asked to look at the two signals here and what are the amplitudes and period of those two signals. So that's part C, and then based on that to design a PI and D controller using the Ziegler-Nichols rule given up here. So either PI or PID, they both operate on the same assumption that in order to do that I need to know the ultimate gain, KU, and I need to know the ultimate period, TU. Right? The ultimate period, TU, is going to come from part C, okay, because I'm determining the period of the signals y of s and u of s. So once I do part C, I'm going to know this period. And as part of that, we can also figure out the ultimate gain. So I guess that's the idea of using the relay is I guess the practical way in which we go about doing this Ziegler-Nichols test, the ultimate cycle, because once I put in a relay, my output is going to oscillate and the relay is going to go on and off. So that if we were to sketch the nature of the signals at those points, that's what they are going to look like. They're both going to be periodic. The relay is going to be switching on and off, and my output is going to be oscillate. Because I guess that's what's going to happen. So what we're asked to do here is figure out the period here, TU, and that's going to be the same as the period here, even though I didn't quite sketch them the same. Those would be the same, so there's no difference. So if we were to look at them, they'll be, we'll get exactly the same period. The amplitudes at this point, we know are plus and minus m. We're told that from our relay. So the amplitudes on my signal coming out of the relay is going to be minus m to plus m. And what I'm asked to do, I guess, or part of what I'm asked to do, is calculate the amplitude of this signal, so we can either go the peak to peak or half it doesn't really matter.
But if you pick up the halfway, should you multiply the answer by 2?
It doesn't. In terms of me correcting it, as long as I'm clear that you understand that it's half of it, so you write, you label it on your answer sheet, or you say, look, I'm going to calculate half of it, then that's fine by me. Yes, so that's fine by me. As long as it's clear which of the two of them you're going to do. So in terms of, I guess, the working through this, or describing functions, what we're saying is if we want to linearize this, we can do so. that the equivalent gain of this element is 4 times m over pi times a. M is indicated on the diagram. That's the plus and minus m coming out of the relay. On slide 5 there, can you indicate what or where you would find a? So in terms of this formula here, we have 4 times m over a by pi, or pi times a, whichever is more convenient for you. Where's a?
Is it the amplitude or the total amplitude?
Okay, so it is an amplitude. At which point in the loop are we going to find this? So like we have an amplitude here, 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 and here. So we have four possible different ones.
Is a beer or would it be a beer or before dm?
So we have take a vote. So some of us are saying it's y of s or it's e of s. What do you think?
It's not the same thing,
Is it? I'll come back to whether it's the same thing or not in a minute, if you don't mind.
Yeah, it's half one.
People justify by 0, then you say that R of S is 0.
Okay, so even if, I guess, part of the clue is given in the formula here, so that our describing function is looking at the ratio between two signals, u and e. E is at this point. So it's looking at these two signals. So technically, A is associated with the amplitude of the error signal. We're assuming that the error signal is a sinusoid. So that's assumption 2. The input to the nonlinearity is a sinusoid. So the shape of that signal, if we were to plot E of t, we'd expect it to be doing something like this. Right? And A, then again, is half that amplitude. So that's what we'd expect A to be. So in terms of our formula, we've got 4 times m over pi times a is the formula. M is the amplitude of the output of the relay, and a is the amplitude of the signal going into the relay. One of the common stroke questions that was made is y of s, and so does it matter in this case whether it's the error, the amplitude of the error, or the amplitude of y?
No.
Why?
R of S is 0.
Okay, so my error signal, thank you, E of t or E of s, it doesn't really matter, is my reference minus my output y of t. We were told in the question that r of t is equal to 0. So therefore E of t is going to be equal to minus y of t. So with the exception of the sign, right, the amplitude of that signal is going to be the same. Okay, so the minus is obviously just going to flip it. So assuming it's centered around 0, then the positive bit becomes negative and the negative bit becomes positive, but I'm not changing the overall amplitude. So in this case, because we're saying r of t is 0, it actually doesn't really matter that much whether we take the measurement from the error or from the output. E is going to be equal to y in terms of the amplitudes in this scenario because r is 0.
What's the value of minus yt? Does it mean that our sinusoidal is in the opposite direction?
Yeah. So if we were to, so if that was E of t, then if we were to flip it, y of t would look like this. So it would be just inverted. But we've still got the same amplitude from, if you think of peak to peak or from 0 to peak is going to be the same.
signal going into the controller, is it? It's a flip signal.
Yes. Yeah.
So with your question last time, you asked which of them are working from E of t or Y of t, just to make it specific.
So in theory, we're supposed to be using E of t. We're looking at the amplitude of it. And what I'm saying in this case, because R is 0, it actually doesn't make any difference whether we go with E or Y, because we're going to have the same amplitude. Because one is just the other signal flipped. We're not changing the amplitudes. So it really doesn't make any difference. So the idea is, in terms of our describing function, that we're replacing the relay, or we can replace the relay with a linear element, where the gain is called this gain, where the gain is equal to 4 times m over pi times a. And we also know that when we do that with our relay, my closed loop system is going to oscillate. So if we think of the equivalent linear system, then that means the gain at which it's oscillating is what we call the ultimate gain. Right? Because that's the term that we apply to it. So if we have a linear system which is oscillating, the proportional gain which causes that to happen is called the ultimate gain. The idea is then, if I can figure out Ku, so if I can work out Ku, so if we can work out Ku, the gain at which the closed loop system becomes unstable, I know then that Ku is going to be equal to 4 times m over pi times a. And then I can figure out, for example, a, the amplitude of the error signal. So the sort of steps that we need to do to solve this is we're going to use. Do any of you remember the Routh-Hurwitz array? Well, okay, I'll rephrase that. Did any of you ever hear about the Routh-Hurwitz array? No. So, exactly, John Horn. Yeah? I don't have any expectations. There's a difference between things, which is why I rephrased it from do you remember to maybe have you heard of. One of the things we're going to use, or one of the things that we need to do, is if we want to determine the gain and the period of the oscillation, we can determine this from this Routh-Hurwitz array, which is just a numerical technique to figure out those things. As I said, once we know that, and if we know m, we can figure out a, and we can then figure out the amplitudes and periods of the various signals. Okay, so from here we'll figure out the period, and then we can figure out the amplitude, and then I know u of t and y of t, which are the two things that we were asked for in the question. So, to do Routh-Hurwitz, and again, if you were to be asked this in the exam, what will be on the end of the appendix is this slide 8, right? So I'm not expecting you to remember the Routh-Hurwitz array and how we, and to remember the coefficients. What you need to, or you'll be given slide 8 so that you can use that to create the array, because why would you remember it, I guess. So, the first thing that we need to do, the Routh-Hurwitz is based on the closed loop transfer function, because we're assuming that we have a closed loop system, we've increased the gain until it becomes unstable, and we want to figure out what that gain is. So first things we need to do is calculate the closed loop transfer function. So if we go back, sorry for jumping around there, so if we look at our system, my transfer function is 1 over s plus 1 to be cubed. So my model of my system is 1 over s plus 1 to be cubed. So when I multiply that out, I get s cubed by 3s squared plus 3s plus 1. Right, and obviously you need to do that first of all. We then need to calculate our closed loop transfer function. And I'm calculating my closed loop transfer function for the system that's shown there on the bottom of slide 6. So that's where I'm assuming I have increased the gain until it becomes unstable. So this one here. So the proportional gain that I'm using is called Ku. Now I don't know what the value of that is at the moment. The objective is I need to find that value. So I don't know what, for example, is it 4 or 10 or 20 or what number in here makes the closed loop system unstable. So we're just labeling it Ku at the minute. So my controller is Ku. My closed loop transfer function is given by C times G over 1 plus C times G. And then we want to calculate the closed loop transfer function. So, in 3 minutes, can you do that for me? You're going to keep that variable. We don't know the number, so your proportional gain is just Ku. So you need to substitute. So you need to use that variable in your calculation. G of S, you know, is 1 over S cubed plus 3S squared plus 3S plus 1. Ku is my proportional gain. What does my closed loop transfer function look like? And it is going to have that variable Ku in the middle of it someplace. Okay, the 1 over S plus 1 to be cubed I've worked out for you, so you don't need to work this bit out. So the 1 over S plus 1 cubed is going to give us 1 over 3S squared, 3S cubed plus, sorry, S cubed plus 3S squared plus 3S plus 1. Ku is your controller gain, and you want to work it out. One term above the line and one term below the line. What's the difference? Okay, we don't have tau. Not quite, no. Okay, so if we figure out C by G first of all, which in this case is reasonably straightforward. I think it's KU by the transfer function, which is just going to give me KU in the numerator. So it's going to give me KU over S cubed plus 3S squared plus 3S plus 1. And then C times G over 1 plus C times G means that I'm going to get KU over S cubed plus 3S squared plus 3S plus 1 divided by 1 plus that. If we want to simplify that, then we have, for example, a common term in each of the denominators, or the term that's common in each of the denominators, so these two. So if I multiply above and below by that, and then going to get KU on the top, because multiplying cancels out with one that's dividing. I get 1 by all that term, so I'm going to get 1 by S cubed plus 3S squared plus 3S plus 1, and then I'm left with the KU here plus KU. So my closed loop transfer function is going to look like this in this case.
You couldn't divide or multiply above and below by the inverse of that top fraction, no? Is that wrong?
You should get the same thing.
Yeah, I did that.
No, but I guess you still have a fraction in both parts of it. Yeah, it's going to. Yeah. There's nothing wrong with what you've done, just push yourself to the next step.
If we do have a number in normal transfer function, normally you should have the tau x, 1 over tau x plus 1.
Yes, for a first. Yes, and in this case you do. So the tau is 1 in this case. So if I look at my transfer function, 1, the tau would be appearing here. So tau is equal to 1 in this case. Yeah? Yeah.
That's the KU times 1 over that. So can you not just do 1 over that? Doesn't matter.
No, one last question.
No, that's cool. It's just, I felt it. You are right.
One over it doesn't have like the argument. Yeah, but you want. There's nothing wrong with what you did, but it just doesn't help us because I still end up with a fraction here. I'm ending up with something here. So the idea of multiplying is that I get rid of the fractions. Well, the two bits of fractions, and I end up with just one, a numerator and a denominator. Okay, so in terms of answering or starting to answer the question, part C, right? Calculate the given the closed loop system, determine the amplitude and period of the signals. Right? The assumption is my closed loop system is oscillating. The gain in which it's going to oscillate is the ultimate gain. In order to figure that out, I must first calculate my closed loop transfer function. Right? Guess what step is most frequently missing when we ask this question in an exam? Calculating the closed loop transfer function. It's the first thing we have to do. Right? We can't go off, well, you can actually answer it without doing it, but you really simplify the question, and lots of the time it doesn't work out and you get nonsense answers, okay? Because you didn't calculate the closed loop transfer function. So in terms of numerically working through this, the first thing you have to do is calculate the closed loop transfer function in terms of figuring out those amplitudes. Right? Once we've calculated the closed loop transfer function, we can then come along and use slide 8, which is our Routh-Hurwitz, because Routh-Hurwitz is based on I guess, looking at whether an equation is stable or not. And that really makes sense when we're looking at the closed loop system. So we're looking at the denominator of my closed loop transfer function. So I'm looking at the s cubed, 3s squared, 3s, and the 1 plus ku bit. We're going to use this Routh-Hurwitz array. And the argument is that we construct this array, and we'll talk about constructing this in a minute. We look down through the first column, and if the first column is all positive, or technically if there's no sign changes in this first column, then I've got a stable system. Right? Or what we do, if we want to figure out the gain that makes it unstable, is we're going to look down this column, and we're going to figure out when one of these coefficients becomes 0, because then I'm looking at the sign change. It goes from positive to 0, for example, and the next bit would be negative. So once we find where one of those first columns becomes 0, then that's going to give me the ultimate gain. To construct the elements, we're looking at the denominator. So we're looking at the s cubed and 3s squared plus 3s plus 1 plus ku. We're looking at this bit of my equation. S to the n is the highest power of n in my denominator, so in this case it's s to the 3. The next one is s to the 2, and then I have s, and then I have an independent coefficient. Right? The array is going to have s to the n elements, so there's going to be n elements. So if n is 3, I'm going to have 3, 2, 1, and 0, so I should have 4 rows in my array when I've constructed the thing properly. Right, so again, by looking at the power here, I know how many elements. So when I've done that correctly, I should have an s to the s cubed, s square, s to the 1, and s to the 0. Okay, so I'd expect 4 rows. Right, and then we're constructing this array. We're starting with the highest power, the coefficient associated with the highest power, a to the n. The next term, we're skipping one, so it's a to the n, we're skipping this one, and then we're taking the next one. So it's the first term, and then we're skipping one, and then the next one, then you'll be skipping one and taking the next one. And our second row then is created by taking the ones that are left out, I guess, or that are not there. So the first 2 rows, in our case, we're looking at s to the 3, so the coefficient of s to the 3 is 1. So it's 1 is the first element. I'm skipping the next coefficient and I'm taking the one after it, which is going to give me 3. So the first 2 rows we can write down just from the denominator, from the polynomial that we're dealing with. So a to the n minus 2, a to the n minus 4, and so forth. So we're taking every second term, starting with the first term. In the next one, then we're taking every second term, but starting with the second one. Okay, so a to the n minus 1 is the first coefficient. So again, that's 3 here. Actually, if we do that in color, just to make sure, so that 3 here, and then I have 1 plus ku. So the second row is going to be 3 and 1 plus ku. So we're taking those 2 terms in my equation, my polynomial.
Is it not 3 and 3? Or is it 3s?
So the first row is formed by taking these 2. So we start at the highest, we skip the next one, and we take the one after that. So that's the 1 and 3 here. And then we're starting with the next term, the 3, and we're taking, and this 1 plus ku has no terms in s. So it's regarded as one term. It's independent of s. So it's the terms associated with s to the 3, the terms associated with s squared, the terms associated with s, and then those without any s or with s to the 0, whichever way you want to think about it. You're just going to have to go with this one. There's no explanation, or at least the explanation is not somewhere where you want to go. Right? It's just a numerical technique for figuring out the value of gain in which the closed loop system becomes unstable. Right? Like the simpler solution is you just use MATLAB, or you just go online and there's plenty of equation solvers which will give you the answer. But in the absence of being allowed to do that, you have to work it out by hand. So the way we work it out is through this. Once we have those first two rows written down, right, so they are written down directly from my equation, then I'm using the ones over here on the right hand side to form my b's. Right, so basically each term is obtained, so b1 is a to the n minus 1, so the first coefficient here by a to the n minus 2 minus a n 0 by a n 3 divided by a n minus 1. Right, so in this case it's 3 by 3 minus 1 plus ku divided by 3 is going to give me that term. So s to the 1 is 3 by 3 is going to be 9 minus 1 plus ku all over 3. Because it's an minus 1 by an minus 2, so it's this one by this one. We multiply those two, so that would be 3 by 3. So we basically we multiply these, we subtract this, and we divide by this.
Like a matrix.
Yes, like as in calculating the determinants of matrices, that same idea. But again, if you've actually forgotten that stuff, don't worry. Right, try and think of it. We're applying B1 is calculated by this. So it's a minus 1 by a minus 2. So this one by this one, minus this one by this one, divided by this one. So we're just applying this formula. Our last coefficient here, s to the 0, which is labeled C1 there. We're going to calculate in the same way, so it's going to be the first term of S1 by the 1 plus Ku minus 3 by 0 divided by this term, which is just going to give me 1 plus Ku, which is just going to give me this term over here. And again, you can work that out yourself if it's not immediately obvious. The term here will be 0 if you work it out, because we're assuming these guys over here are 0. So if we calculate this one, it's going to be 0. So then in the formula for this, we'll have B1, this term will be 0, so we'll have B1 times an minus 3 divided by B1, which will just give me an minus 3. So we'll just give me 1 plus K.
X1 you calculated equals to U1.
So that's
The S1 and now this is is 1, getting from B1.
Yeah, from the formula B1. Yes.
And why is B2 left out and B2 from C1?
You can calculate it. So if you calculate this, you're going to be doing this by this term, minus this by this term, divided by this. These are 0, so this by this is going to give you 0, minus this by this is going to give you 0, so this is going to be 0. Don't worry about here. So the number of sign changes in the first column of the array is equal to the number of poles in the right half plane, so the number of unstable elements, the number of unstable dynamics.
And we can tell that by looking at it, can we?
Yeah, so we're going to look here at our first column, right? So that's your array. So then, if, for example, if 1 plus KU is equal to 0,
Should it be minus 1 plus KU brackets?
should. That's where I was. Thank you. Okay. So the idea is we look at the first column, and if there's a sign change in the first column, so the first two elements are positive. So the idea is if this becomes 0, so if we want to figure out the gain at which makes the system become unstable, we can look at the gain which will make this term be equal to 0. If this becomes equal to 0, I'm right on the border. If KU becomes larger than that value, then this term here will become negative. So for example, if KU is 9 here, then I get 9 minus 10 divided by 3 is going to give me minus 1/3. That's negative, so I've gone positive, positive, negative. And the condition for stability is that all the terms in this column are positive, or alternatively, if we go down through this and count the number of positives to negatives, then that will tell me how many poles are unstable. So if we think of our S-plane, and we've got our right half, then any poles that are over here are going to result in an unstable system. And that's indicated in our Routh-Hurwitz by sign changes in this first column. So if this term or this term becomes negative, right, I've got an unstable system. If I find out where these two are equal to 0, so this term is equal to 0 and this term is equal to 0, I've got my marginally stable condition. I'm just on the boundary between stable and unstable when those terms become equal to 0. Right? So from the last row, from the S to the 0, I've got 1 plus KU is equal to 0. So one condition is that KU is equal to minus 1, but we don't usually consider negative gains. From S to the 1, I've got 9 minus 1 plus KU over 3 is equal to 0. There should be brackets around the 9, 1 plus KU, which when I work it out gives me KU is equal to 8. So KU is equal to 8. So we usually ignore negative controller gains. So KU is equal to 8 is the gain at which my closed loop system will become unstable. And once I've figured out KU, I can then figure out the period. Actually, we'll go back here. So if I take the gain which makes my closed loop system unstable and substitute it back in to my closed loop transfer function, then I'm going to get 8 over s cubed plus 3s squared plus 3s plus 9. So for this closed loop transfer function, my closed loop system should be oscillating. Okay, so I should be seeing a continuous oscillation because this is the gain which makes that happen. And if I want to figure out the period, which is part of the question, what's the period, then I can make a substitution. I forgot to change j's to i's there, so this is getting the frequency response, or looking at the frequency. We make the substitution s is equal to I omega. We substitute that there into the denominator. So 3s becomes 3 times I by omega. S squared becomes minus omega squared, because I by I gives me minus 1. And s cubed then becomes minus I omega cubed, omega u cubed. And for example, we can, here we have real terms, minus omega u times squared and 9, and imaginary or purely imaginary terms.
Sorry, what happened to the 3 on the square?
I forgot all about it. Yes, I forgot about it. So there should be, thank you, there should be a 3 omega u sitting in there.
Why did the I disappear? Say it again, sorry.
Say that again?
Why did the I disappear?
Yeah. So why did I disappear in the s squared term? So I is equal to the square root of minus 1. So if I square that, I'm going to get the square root by the square root, which is just going to give me minus 1. If we want to figure out when it becomes unstable, we look at when the denominator will blow up, so when it will become 0, so we can take either you'll get the same answer, the imaginary elements or the real elements, and we solve for 0. So the idea is if they become 0, then I get 8 divided by 0, which is going to give me infinite, and therefore it's unstable. So for example, if we solve this, we'll get omega u is equal to 3, and therefore omega u is equal to 1.73. Okay, so we can take, looking at the denominator, I have terms in I, or I have independent terms, there should be a 3 there. I can take either of them, I'll get the same answer. Let it equal to 0, and solve for that, so I get omega u is equal to, for example, 1.73 in this case. If I know my frequency, I can figure out the period in the first line, 2 pi over omega u. So the period of the oscillation is going to be 3.63. So if we go back and back and back and back. Part of the question, C, given the closed loop system, determine the amplitude and period of the signals y and u. Started off by saying these are going to have the same frequency. I now know what that frequency is, and therefore I know what the period of those are. So we calculate the closed loop transfer function. We use Routh-Hurwitz to determine the ultimate gain. I substitute that back in, and I can solve then for the frequency omega u.
You didn't tell me what the other two terms in the denominator, no?
If you chose them, you'll get the same thing. Because you'll get omega u is squared is equal to 3. Because you'll have 3 here and 9 here. So when you divide across, you get minus omega. So omega u squared is equal to 3, and omega is omega u squared is 3. So it doesn't matter whether you take the imaginary or the real terms, you get the same answer. So there's our period. I think in the question it was probably omitted, but if you're told what the amplitude m was, so for example that m was equal to 5, then knowing Ku you can easily, and we do know Ku, we just calculated it, we determined that Ku was equal to 8. This is our describing function for the relay. We know what Ku is equal to 8. If you're told what m is, so I think it was missing from the question, but let's say for argument's sake it's 5, then we can solve that for a and get that a is equal to 0.8.
Does it matter between 5 or 10 in that case then if m isn't stated?
Do that again?
If you're not told what m is, can you pick 5 or 10?
If m would need you, well technically you can't answer it if you're not told what m is. So you can do what you want. You can just, you should have told us what m was, and that's the end of it, or as you said, choose a value. But no, you will be told. No. It's on one of them, but I'm not going to be asking that because we're a week behind what we're going to be now. The last part of the question is really straightforward. Once you know the last part is to calculate Kp and Ki, or Kp, Ki, and Kd, it doesn't matter. To do that, you need to know two things. You need to know the ultimate gain, and you need to know the period. Okay, we've just calculated the two of those things. Right, so, and then your formula is Kp is 0.4 times Ku, Ki is Kp over 0.8 times Tu. And as I said, we have slide 12 has the period calculated, and slide, I guess that's 10, is it? We worked out the ultimate gain, Ku.
Would you tell us what kind of controller you want, or would that tell us?
You can assume it'll be Pi. But either way, it's just a row off the table. Okay, we leave it there and take a break for 10 minutes, and then as I said, if you can be thinking of, if you have questions related to Wednesday or Wednesday's assessment, then I'll be happy to deal with those when we come back.